Hello everybody and welcome to Operations Research course. And now we are in the final chapter of the course, chapter 12, and this is a look under the hood. So far this lecture has been basically linear models. So we have this GLPK hammer that we use to solve different problems, and the problem was always to modify or model our given problem as a standard form LP and then solve it with GLPK. And now we look a little bit under the hood of the GLPK, so we explain a little bit what happens when you type GLPK this and that. So what happens on what happens there basically. How does the computer solve these problems? And as true Dune methods here, so in the Dune universe, you know the thinking machines and the computers, they are banned. Everything has to be done by hand. So in this chapter, we calculate things a little bit by hand, and hopefully by doing so we appreciate the computers. So you really don't want to calculate these things by hand. But let's see, maybe it's instructive to do it a little bit. So in the first part, the title of the first section is called "The Truth is in the Corners." And in short, what does this mean? So we have recall that we have a standard form LP, so each LP can be written in this form, so it's a maximization of something where we have only upper bounds and we have sign constraints for the decisions. Now, if we forget the objective function and only look the constraints, so ax is less than or equal to b and x is bigger than or equal to 0. So those x's that satisfy these conditions constitute what is called feasible region. So this feasible region is some kind of area in this n-dimensional space. So n-dimensional since we have n decision variables. So feasible region are all those possible x's that are solution, not necessarily optimal, any solutions to this problem, any meaning it's not the maximization, it's just some x that satisfy these conditions. Now it requires maybe a little bit of imagination, but in this n-dimensional space, this feasible region is an n-dimensional polygon. You know, polygons are like cube or tetrahedron or dodecahedron or pyramid shape. These are polygons. So the polygons are you have edge points and then somehow those edges or corners of this polygon generate the whole polygon. Okay. And what is now a thing that I don't prove, but it can be proven, and what is the kind of fundamental thing here why everything that we will soon tell works is that the optimal values, so let's call them x star of this LP. So x star is any such x that satisfies these constraints, and the maximal value of z is given by c prime x star. So these optimal values of this LP, they are in the corners of this feasible region. That's a fact. Not all corners are optimal, but if you find if there is an optimal solution, then the optimal solution is found in one, maybe many corners have the same optimum, but in the end the optimal solution is in the corner. It's not in inner point, it's not on the boundary only, it's in the corner. Okay. So before we investigate further the implication of this fact that the optimal is in the corner, let us reformulate this slightly. And The idea in this reformulation is that inequalities are nasty, equalities are nice. You have probably learned this in school. When you have to solve inequality, it's not so nice as solving an equality. So we turn these inequalities into equalities, and the trick how to do this, I think we have seen this before, is to consider so-called slack form. So if we have something like this, then if ax is less than or equal to b, then it means that this is maybe equal, or maybe there is something positive that is the difference. So I can formulate this equivalently by using so-called slack variables s's. So maximization is what it is, but then ax plus s equals b. Okay. Well, as the name tells, s means how much there is slack in this inequality or set of inequalities, and s's must be positive because there is an upper bound, so there is a positive number here. That's a difference. b minus ax, so s is b minus ax, of course. But formally, solving this problem is the same as solving this problem. And we can actually write this, if we wish, in an augmented form. So we have extended decision variables, so s's and x's. I write this as x bar, so x bar is decision variables, and then we have, so there should be a little space here, sorry about that. We have decision variables and then the slacks. So then this can be written as a simple maximization set objective like this, technology matrix like this, and equality, and then yes, this augmented decision variables have to be non-negative. So this form is equivalent to this form, and this form is just this form, and this form are the same. They are just written in a slightly different way. So the whole point is then that in order to solve this, we need to only look at the corners. So we omit the non-negativity constraints and solve this kind of system. So this is the basic idea now, to find the corners corners of this system or the feasible region. We just solve this equation for x's and set some of the decision variables 0. Those then the so-called free ones or basic variables, they mean the corner. Okay, this is, I know that this is a bit abstract now, but we will have an example that will explain this very concretely what's happening. At this point, somehow just understand that this a plus I x bar equals b, solving these x's here corresponds to find the corners. And how does this happen? So this equation has now n plus m variables. So n for each decision plus m, these are the slacks, these were the constraints, and there are m equations. So this is ill-determined in the sense that it has many solutions because there are so many variables and only so many equations. So there are n plus m variables and m equations. So this system has many solutions, and each solution is a corner or almost the corner of the original feasible region. So what does it mean? We have m plus n over m solutions. So these solutions are found by setting certain variables zeros and the rest solving it with respect to the rest of them. So this means that if we have an LP with 3 decision variables and 4 constraints. Then the system has 7 over 4, which is 7 factorial divided by 4 factorial, 3 factorial, that is 35 different solutions. Okay. Again, I explained this a little bit. So all the corners of the original LP's feasible regions are some solutions of this system that I have here. There are some solutions of this system that are not solutions to the original one. We see that too soon. And how we find these solutions, again, I explained this a little bit. Let me explain it again. So we choose m components. So m is the number of constraints of the x. So these will be the basic variables. So for each constraint I choose a basic variable, and then the remaining components of this x, the remaining decision variables or augmented decision variables, are set to be 0. Okay. Then I have one variable for each constraint, meaning that now the system is balanced, so I will usually have exactly one solution. And this this solution, if it is given like this, that I have first set some, I've decided that some m components are the ones that I want to solve. These are called basic variables, and the rest are called non-basic variables. The rest are set to 0, and then I get the solution, and this solution is also called basic feasible solution. So this is the way I go through check all the corners. Okay, this was maybe a little bit confusing. Let's look at an example so we can really see what's going on here. So example 12.4, checking corners. So I consider the following kind of LP. So now I'm given it in standard form. I could have started with the non-standard form and then transformed it to standard form. But let's have this exercise or example not unnecessarily long. So here I have a standard form LP. So I transform it first into a slack form. So it means that here I have upper bounds. So this plus some slack S1 equals 40, and here in the second also some variable, now it's slack 2. Slack 1 is for the first row, slack 2 is for the second row. So now I have this standard form LP written in a, if you like, standard slack form. Okay. And then let us solve this system. Now this is some kind of mistake. I'm sorry, but I have to think about a little bit what's here. Yes, so this shouldn't be here. I make a correction to the notes soon, and don't then be wondered if this is missing, because this is a typo. This simply shouldn't be here. So omit all this. So we have this slack form here, and we have to choose it by finding all the corners. And how this is done, so we have now m is 2 and n plus m is 4. So we have 2 equations and 4 decision variables. So decision variables, 2 original decision variables and 2 slacks. So the augmented vector would be x1, x2, s1, s2. So this would be the x bar we had. So we solve this by choosing always two variables to be basic variables, and then the two are set to 0, they are the non-basic variables. And this, to explain how this goes, so let's hope you can read this. So there's a table and there's a picture. So first I take slack1 and slack2 to be the basic variables. So x1 and x2 are zeros. So x1, x2 are zeros. And then this is the system of equations. And I can read immediately here that s1 is 40 and s2 is 60. So I have one basic feasible solution here with x1 0, x2 0, s1 and s2 are 40 and 60. Then I check whether this is a basic feasible solution. It actually is. Don't worry about this yet. Then I can calculate the z, what is the objective value of the function. With this it's 0, and then the pt here as point, it refers to this picture. So we are looking f, so we are looking at the origin, this point here. The feasible region, you can see it's a polygon, is this kind, this green region here. Okay, so that was the one corner. Then I take x2 and s2 to be the basic variables. So here I have again the same equation. So this always, this is equal 40 is equal to 60. What is here is what is here, but I have set the non-basic variables to be 0. So here x2 is what it is, and here is what it is, s2 is what it is, but s1 is equal to 0 and x1 is equal to 0. So it's this kind of system. So x2 equals 40, 2x2 plus s2 equals 60. This can be solved easily. We get the solution. So x1 is 0 and s2 is 0 because they are non-basic variables. Solving for x2 and s2 we get 40 and minus 20. And now it happened that we get a corner that is not feasible. So this is not a basic feasible solution because it corresponds to point A here. So point A is actually here. The reason why this was not a BFS basic feasible solution was that in solving this turned out that this S2, which is slack, is minus 20, but the slack has to be positive. I have simply omitted the non-negativity constraints here, so I have to check additionally whether the solution is feasible or not. So this was not feasible. Okay, so the rest goes the same way. So let me just take the, I'm not going through all of them. Let's check the optimal corner actually, which is the corner E. That's the last one. So there I've decided that x1 and x2 are the basic variables, BVs. So the non-basic variables will be the slacks. So the slacks will be 0. So now I'm solving the original equation. x1 plus x2 equals 40. x1 plus 2x2 equals 60. Again, this pair of equations is easy to solve. Two equations, two unknowns. I get x1 20, x2 20. So s1 and s2, they are both zeros since they are non-basic variables. Is this a basic feasible solution? Yes, it actually is, because all these are positive. And it's this point E here, and there I get the objective value 140. So in this way, looking at all the possible ways of setting BVs and NBVs, we go through all the corners and some extra corners already also. Then we just check the value of the optimum at each corner and choose the biggest one. And we see that the biggest one is 140, corresponding E point here. So we have found an optimal solution. x1 equals 20, x2 equals 20. So that is one way of solving LPs. So we simply check all the corners. So looks like a lot of work, and yes, it is. And then we can ask whether it's reasonable or not. Let's get back to that soon. Before going further, let's consider exercise 12.5. So in exercise 12.5, check the corners. So this is related, of course, to this example 12.4. So in 12.5 you are given LP like this. So it's a minimization now. And double inequality is there also. And you should solve this by checking all the corners. And yes, well, how do you do it? Well, hint would be transform first this LP into a standard form, then the standard form into a slack form, and follow the hints or the ideology or what happened in the example 12.4 above here. So in the end, once you have a standard form, turn into slack form, and then build a table where each row corresponds to a corner like this. So that was exercise 12.5, hard work. And then the next question is, so you can pretty much quickly see or now understand that if I have more variables and more conditions, then there are more and more corners to check, and this becomes very tedious and you have to do a lot of work. But then you may think, okay, we have fast computers, so what? Let the computer do the work. But unfortunately, there is thing called combinatorial curse. So this combinatorial curse is a thing that happens in many places in mathematics and computer science. So this is the remark 12.6. So it seems that we have a very simple algorithm to find the optimum. Just check all the corners. And so if we have a LP with n decision variables and m constraints, we go to the slack form, then we have the corners that corresponds to now these red dots. How many do we have? Then we have n plus m over m. So how does this number behave? So here it's the same number written in a factorial form. So suppose we have 15 decision variables and 15 constraints. So how many corners we have? We have 15 plus 15, that's 30 over 15, and that is already over 150 million. So certainly you are not going to do this by hand. So this is a huge number to do by hand. But of course, who works by hand? We have computers. So then you can think about, suppose you have a computer that checks 1000 corners per second. So is this fast or slow? I think it's pretty fast for today's computers, but and outright impossible if you use Java or Python or any other not so efficient language. If you use C, then maybe it's possible. So it means that then it would take almost 2 days to check all these corners. So you may think that, okay, so what? Not a problem. 2 days, that's not too long. Let the computer calculate. And you may think that, okay, 15 decision variables and 15 constraints. This is a big LP. In practice, you will never have something like that. Well, think again. Now, the thing is that 2 days may be a very long time. So if you want to optimize, say, your portfolio in a stock exchange and you are doing high frequency trading, you don't want to have the solution in 2 days. You want to have it now in a milliseconds or maybe seconds, but certainly not. You are not going to wait for 2 days to rebalance your portfolio that you are going to rebalance daily or in hourly or even within a few seconds. And then how about this number of decision variables? 15 decision variables and 15 constraints. Now, this is not big. Let's have this stockbroker as an example. It's not unreasonable that this stockbroker has something like 50 stocks wants to trade. That's not so much. And maybe easily 50 constraints to constrain the trading, that you don't want to your risk exposure to be bigger than this or that. They give you constraints. So 50 constraints and 50 stocks, 50 decision variables, not so big. Or you can look at your local kiosk inventory, how many different products there are and what kind of constraints there are. Easily 50. All right. So let's have this. We have say this broker, 50 constraints, 50 stocks, supercomputer that checks 100 million corners per second. Maybe someday computers are this fast, certainly not yet. How long would it take to check all the corners? It would take something like 6.89 times 10 to the power 44 years. And the universe is not that old. And I doubt that the universe will last that long. Well, nobody knows what happens to the universe, but this is an astoundingly big number. It's not even there are not that many atoms in the universe. So the bottom line is, so checking the corners would simply take too long. There is no point of trying to do that. So then you might ask, why did I show you this picture here? Well, this picture, of course, this was to build the intuition to understand what's going on there theoretically. And yes, I even have the one exercise for you to do this manually once. But please understand that this idea of checking all the corners is infeasible. It will take simply too long for any reasonably sized LPs. Of course, the LPs we had here in this course are so small that you could probably do this with computer, not by hand. So that was the introductory story of looking under the hood. And in the next video lecture, we look what do we do since we don't want to check all the corners. So what is the alternative? And the alternative is the so-called simplex algorithm. See you.